Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Yeah, hello and a warm welcome to the Trustworthy AI webinar series. My name is Wojciech Samek. I'm professor at TU Berlin and the head of the AI department at Fraunhofer Heinrich Hertz Institute in Berlin. And it's a great pleasure for me to present our speaker today, Irini Luzi. Irini is a full professor for open source intelligence at the Bundeswehr University Munich and the Research Institute for Cyber Defense and Smart Data, where she is leading the AI ML lab since August 2022. Prior to that, she was professor of AI at Free University and also a professor of intelligent systems at the Leibniz University of Hanover. Irini is an expert on fairness in AI, and I very much look forward to your talk on how to make AI more fair and unbiased. Irini, the floor is yours.
Thank you very much for the nice introduction and for the invitation, and thanks to the audience for being here. It's my great pleasure to talk in this session. And let me share my screen. So I hope you can see my screen. I assume so. Yes?
Yes.
Okay, super, thank you. So the original title of my talk was how to make AI more fair and unbiased, but thinking about it, I think it's better if we are, let's say, more pragmatic about what to expect. So I replaced the unbiased with less biased, right? So how to make AI more fair and less biased. This is the topic of my talk today. So I think we all agree that we live in great circumstances for artificial intelligence. We have huge amounts of data, complex data, we have good algorithms, we have good infrastructure to train our models, and we have participation, so everyone wants to join, and everyone has the tools, so data and AI tools, actually libraries, etc., to work with AI nowadays. And we all benefit from the many successful applications of the technology, from information filtering to recommendations to navigation, automation, etc. But we cannot ignore that in parallel to these successful applications, there are also a lot of other applications and a lot of institutions incidents which raise concerns about the technology, what is this technology doing, how it affects our lives, and also discussions about what sort of technology we want to have, we want to develop. And I categorize all these different cases, so here are just some representative examples as failures of the technology. And the only reason for highlighting these failures is, I think, because we can learn from these failures and we can actually use these failures in order to improve the technology. So there are many different examples here and they relate to different types of failures. So today I will talk about one particular, let's say, type of failure, which is related to the discriminating impact of the technology. So there are a lot of incidents lately. Probably you have read about them or heard about them in the news, etc., about the discriminating impact of AI technology. So how these systems discriminate on the basis of what we call protected attributes, like, for example, gender, race, age, etc. And many of these incidents come from computer vision. So there are a lot of improvements in computer vision in the last years. So in many of these systems, we have performance which is better than human performance or close to human level performance. But this good performance actually holds only for certain population subgroups. So these systems perform very well, but only for certain population subgroups, typically white males, and they do not perform equally well for other population subgroups, for example, Black females. So here is an example of racial and gender discrimination and the famous white guy problem of artificial intelligence, which comes as no surprise because these systems are typically trained with data which depict white people, and also by engineers, by developers, which are mainly white, even white males. Another example is from recidivism prediction. So this is a system used in the US, the COMPAS tool, to predict whether what is the risk of a defendant to commit another crime. And this system predicts higher recidivism risk for Black defendants comparing to white defendants. So here you have an example with two defendants, Brisha Borden and Vernon Prater, and the prediction of the system. So according to the system, Vernon is of low risk, 3, and Brisha is of high risk, 8. But if we look at the actual profiles, then we see actually that Brisha should have a lower risk in comparison to Vernon, right? So this tool reflects historical bias, racial bias against Black people. Another example is on service provision. So this is an example from Amazon same-day delivery. So I think many of us know this service. It's also offered in Europe. And this is a study run by Bloomberg. And what they did is that they compared the areas in which the service was offered in the US. So they compared different US cities like New York City, Boston, etc. And they found that this service excludes many zip codes that correspond to neighborhoods that are inhabited in their majority by Black people. So for example, in New York City, Bronx is excluded, or in Boston, Roxbury is excluded. And the question, of course, was why these areas are excluded. And Amazon actually replied to their inquiry that they don't use race or the zip code in their models, but it seems that the model learns to predict based on race or based on zip code, which in this case acts as a proxy for race. So there are a lot of incidents regarding bias and discrimination in artificial intelligence, but, and I think this kind of explains or justifies all this ambivalence about the technology, right? So the fact that we have all these contradictory feelings towards the technology, and I think we all agree that this is a great technology with great potential, but there are also risks. And maybe this is true for every technology, right? So the example of a knife, is this a tool or a weapon? But of course, the scale of the problem in case of artificial intelligence is uncomparable. It's huge. And that's why there are all these initiatives. I mean, even this series today, it's actually in this direction. So how can we improve the technology? How can we improve trust in the technology? How can we build trust in the technology? So all these initiatives towards responsible and trustworthy AI. And I think actually these aspects of trustworthiness, responsibility should be synonym to AI, right? So definitely we need technology that is responsible and trustworthy. So what you see here is a summary of the ethics guidelines for trustworthy AI developed by the high-level expert group on artificial intelligence. So this is the European view on the responsibility aspects. There was recently also a similar attempt from the US. And what you see here is that one of the main ethical principles is actually regarding fairness, and one of the key requirements is on diversity, non-discrimination, and fairness. So fairness, non-discrimination is actually a very important part of trustworthy and responsible AI. So this talk is about this aspect. It's not the only aspect, as you can see here, but is one of the important aspects. And we talk about bias and discrimination in AI. This is how I started my discussion, but it's clear that this is not a problem that is created by artificial intelligence or is created solely by artificial intelligence. So bias is an old concept, it's as old as human civilization, and it is of human nature for members of a majority group to kind of ignore or be oblivious to the experiences, to the needs, to the concerns of other groups. And that's why in terms of humans, we talk about human bias. So these are prejudices in favor of or against one thing, person, or group compared to another in a way that leads to some unfairness and discrimination. And exactly the same definition holds for algorithmic bias. So it's exactly the same definition. The only difference is now that these decisions are made by an artificial intelligence system or based on an artificial intelligence system. So I talk about algorithmic bias and bias in artificial intelligence. And in this talk, I refer to bias as a negative thing, right? So I refer to bias that might cause discrimination and unfair actions against individuals or groups of people on the basis of protected attributes like race, gender, etc. But bias is not necessarily a bad thing. So we all have our biases, and some of these biases are actually positive. For example, there are biases that keep us healthy, right? So the bias towards healthy eating choices, for example, or there are biases that keep us efficient. For example, if I'm a morning person and I organize my working life so that I do most of the work in the morning, then this is something that actually helps me because it works best for my let's say, a body. And also in machine learning, the term bias is an old one, so we refer to it as inductive bias, and it's a necessary concept for induction. So these are all the assumptions that the model should make in order to be able to generalize, right? So bias is not necessarily a bad thing, but in this case, we talk really about biases that might cause discrimination. So we have this, let's say, bad interpretation of bias. And another important aspect is that bias depends on context. So in my presentation, I use mainly the gender example, and I typically assume that the protected group or the discriminated group are the females, or the women, but this is not always true, right? So in certain contexts, women are indeed discriminated, for example, women in tech, but in other contexts, for example, in ballet dancing, maybe men are discriminated, right? So it really depends on the context. And this context might be also multidimensional. So it's not only about the gender, it might be a combination of gender and race, for example. And also fair is not fair everywhere. So what is fair, for example, in Germany might not be considered fair in some other part of the world. And fairness is a moving target, which means that what is fair today might not be fair in the future, and maybe was not fair in the past, right? So our perception about fairness also changes with time and over space. So the area of fairness-aware machine learning, it's actually a subdomain or a sub-area of artificial intelligence. which tries to develop artificial intelligence methods that do not discriminate based on protected attributes as gender, race, etc. And this is a new topic in computer science. So the topic started in 2008 with a seminal work by Pedreschi, Ruggeri, and Turini. At that time, actually, it was called discrimination-aware data mining. So it's also a terminology drift. So it's not data mining anymore. It's machine learning. Despite the recency of this domain in computer science and in artificial intelligence, actually this is an old domain, and the concepts of bias, discrimination, and fairness have been studied for long in other disciplines, like in philosophy, law, etc. That's why you see a lot of interdisciplinary work also in this field. So it's clear that it's not only a technical problem, and in order to solve this problem, we need also input from other disciplines like law, philosophy, etc. And despite the recency, as I mentioned, there is a lot of work already in the domain, and this work can be broadly organized in three main categories: understanding bias, mitigating bias, and accounting for bias. So understanding bias is really about understanding what are the sources or the causes of bias in socio-technical systems, or systems involving both humans and machines. And how can we observe bias in the data? So how is bias manifested in the data? How we define fairness and discrimination? How can we measure fairness and discrimination? And in terms of mitigation, the main question is really how can we build machine learning models which do not discriminate, or for which the bias and discrimination is mitigated. And there are also approaches which proactively or retroactively account for bias, so in the direction of algorithmic accountability. So let's start with the understanding bias first. So as we know, modern artificial intelligence or machine learning methods, they rely on data, right? So we have data and algorithms. This is how we train our models. So data is a very important part of machine learning and artificial intelligence, especially nowadays. And these data are pretty often generated by humans. So you have human-generated content, like, for example, in social media. Or these data are collected via systems which are created by humans, right? So this means that whatever biases we have as humans, they enter into our systems, and they have been observed in a variety of cases. For example, we have bias in word embeddings. So as you can see here, this is the extreme female occupations and extreme male occupations. So it seems that there is a gender dimension in the different occupations. So women are more associated with occupations like librarian, nanny, housekeeper, etc. And men are associated with occupations like maestro, philosopher, architect, chef, etc. Right? So this is how historically men and women have been perceived, and this is exactly what is reflected in the model. Or likewise for computer vision, as I mentioned before, right? So here is another popular example. On the left, you see an image of Barack Obama, and on the right, you see high resolution image. So this is the PULSE algorithm, where the idea is it takes as input and a pixelated face, and it turns it into a face of high quality, into a high quality image. And we see here that the output is a white man, right? So again, we have an example of racial discrimination bias. And it's not only that these biases, the human biases, enter into the systems, they might be also amplified by these systems, especially complex systems in which both humans and computers or machines interact in very different ways. And maybe the most complex example of such a system is the web, right? So there are a lot of examples of how the web, for example, amplifies polarization, and what are the different aspects that affect the strength of this bias amplification, from model complexity to capacity to accuracy, overconfidence, training data, etc. Moreover, we have a lot of feedback loops and pipelines in this system. So if you think of machine learning system, this is a multi-component system where the different components interact with each other. So they give input, output to each other. And of course, whatever issues and whatever biases exist in one component, they might be transferred and even amplified into some other component in the pipeline. And the typical example here is using using some pre-trained language model, some pre-trained model in general, in a downstream task. For example, in a hiring system, you might use a pre-trained language model to scan the CVs. And if you have now a language model which contains bias, as in the example before that I mentioned, then you can imagine that a man might have better chances for getting a job as an IT architect comparing to a woman, because women are more suitable for other types of jobs according to the biased word embeddings. And there is bias in AI, and this bias might result into harm. And there are two types of harm: allocative harm and representational harm. Allocative harm refers to the cases where a system, the decisions of a system, withhold certain groups an opportunity or a resource. This is typical, for example, in banking, in education, in hiring, etc. And the representational harm refers to how certain population subgroups defined, for example, based on race, class, gender, etc., how they are portrayed, how are they depicted, and what sort of stereotypes are associated with these subgroups. And this is typical for social media, hate speech, disinformation, etc. And let's have a closer look to an example. So this is a simple data set just to showcase the problem. And what we see here is a binary classification problem. So we have two classes, the positive and the negative instances, so plus and minuses. And we have the data plotted in the 2D space with respect to two features. And with color, we encode here information regarding the gender. So we have males in greens and females in orange, and we want to build a classifier. And what is the purpose, or what is the goal of a traditional machine learning classifier in this setting? The goal of a traditional machine learning classifier is to separate the two classes, right? So I want to build a classifier, let's say a line, which separates the two classes, so the positives from the negatives. And we want to find the parameters of this line. And this seems to be a good model, right? So we have a good performance in terms of classes. All the positives, or most of the positives, are on the upper side of the line. Most of the negatives are on the downside of the line. So in terms of class, this model is very good. But if we look now at the gender-specific performance, so how it performs for males and females, then we see actually that all the female instances are actually ignored. Right? So all the female instances, they are on the negative side of the boundary, all the orange instances. So this means that no woman has a chance to get any positive response by the model. And of course, the question is why this happens, right? So if we look at the data, we see that, okay, we have a few women, but actually among these women, we have good candidates, right? So we have positive instances. Half of the orange instances are actually positive, right? So the answer that there are not sufficient, or there are not a good candidates, female candidates, is not an answer here, does not hold in this case. So how is the problem created? So first of all, we see that the female population is a minority, right? So it's not really visible to the model. And moreover, the goal of the model, or what we ask the model to learn, is how to separate the two classes, right? This is the goal of the classifier, to separate the positive from the negative. And we never mention, or we never actually add this extra requirement about the gender, right? So the model is not aware that should pay attention to the gender. This is what traditional machine learning is about. But of course, we want to change this situation. So of course, we want to create models which perform equally well, or well, for both males and females. So this is the typical supervised, the typical fairness-aware learning setup. And the typical fairness-aware learning setup is pretty simple, right? So we assume a batch learning setting. So we assume that we have a data set of instances in advance. And this data set consists of instances which correspond to users, and they are described in terms of different features, so the F features. And there is a single protected attribute. So in the typical setup, we assume that there is a single protected attribute, maybe gender. So we talk about one-dimensional discrimination discrimination or mono-discrimination or single discrimination. And moreover, this feature, the feature S, the protected attribute, is typically assumed to be binary. So it has two values, let's say males and females, and one of these values corresponds to the protected group, so the S value, and the other one corresponds to the non-protected group, so the S hat value. And typically also in this very simple setup, the class attribute is assumed to be binary. So again, we have two classes, positive and negative. And the goal is to learn a classifier, or the goal of fairness-aware classification is to learn a classifier, which is a mapping from the predictive space to the class space, and this mapping should achieve good predictive performance, so it should perform well in terms of the classes, and also it should eliminate discrimination. And in terms of predictive performance, we know how to measure this, we know how to assess this. This is what traditional machine learning is doing, right? So usually we have a loss function. And what about now the discrimination? So we need also a way to be able to measure the discrimination or the unfairness of the model, because this is exactly what we want to eliminate. So for this, we need some fairness measure, and there are many different fairness measures. At least in computer science, there are at least 20 definitions of fairness, and by now I think everyone has understood in this domain that actually there is no single definition of fairness, and as I mentioned in the beginning, fairness depends on context, and different definitions make sense in different contexts. But in general, these definitions of fairness can be categorized into many groups. So we have the group fairness measures and the individual fairness measures. So the idea of the group fairness measures is that the protected and the non-protected groups, so females and males, assuming that gender is the protected attribute. So the idea is that these groups should be treated similarly by the model. So there should be no differences based on the protected attribute. And with regard to individual fairness, the main idea is that similar individuals should be treated similarly. There are a lot of pros and cons with respect to these definitions and whether group fairness or individual fairness makes more sense, and also difficulties associated with the different measures. For example, in individual fairness, the main difficulty is that it's really hard to assess similarity between individuals, right? So how do you define similarity between two persons? But in many cases, a group fairness measure is used, and there are three popular group fairness measures. The most popular one, or the simplest one, actually, is the so-called statistical parity, where the idea is that for both the protected, so S, females, and the non-protected, S prime, the males, the probability of being assigned to the positive class, so Y hat is the predicted probability, so these probabilities should be the same, right? So the probability of being assigned to the positive class should be the same, irrespective of whether you are a woman or a man. So this is the main idea. And as you see in this measure, we don't really look at the ground truth, so it's only about the predictions, and we only focus on the positive class. So the next measure, which is called equal opportunity, tries to look also at the ground truth. So it's not only about the predictions now, but it's about the errors. So there should be no difference in the errors, in the prediction errors of the model regarding the positive class. So both female positive instances and male positive instances should have the same probability of being predicted wrong, right? So the prediction error should be the same for both protected and non-protected groups in the positive class. Again, this measure focuses on the positive class, so there is another measure which is more generic because it looks also in the negative class. So in this case, the idea is that there should be no difference in the prediction errors of the model between protected and non-protected groups for both classes, right? So this is the difference in the positive class, what we denote here by delta false negative rate. And this is the difference in the negative class, what is denoted here by delta false positive rate. So these differences should be 0, and the overall score, which is called disparate mistreatment, is a sum of these two scores. So we have a way to measure discrimination. It's not perfect, right? So we can have a long discussion here about the different measures and which measure makes sense under which conditions, under which context. But anyway, we have some ways to measure discrimination. So the next step is actually how can we mitigate discrimination? How can we mitigate bias, or how can we build models which are more fair, or fairness-aware machine learning models? And as we know, building a model means really having data and algorithms, and the model is the result of this complex interplay between data and algorithms. And in order to make to create or to learn fairness-aware machine learning models, we have different options to intervene for fairness, or to intervene in order to mitigate discrimination. And in particular, we can intervene at the data. So we can make interventions at the data in order to increase the fairness of the model. So these are the so-called pre-processing approaches. Or we can intervene at the algorithms. So we can change the algorithm in order, again, to mitigate discrimination. These are the so-called in-processing approaches. Or we can intervene at the resulting models. These are the so-called post-processing approaches. And as you can imagine, there are also approaches which combine all these steps, or some of these steps. So let's start with the pre-processing approaches. So the main idea here is that we want to intervene at the data, and the intuition is that if we make the data more fair, then the model that will learn upon this more fair data will be less unfair or more fair. So the main idea is to make the data more fair by balancing the different protected and non-protected groups, right? So we want to make them to balance their representation. And the question is, how should we do these interventions? Of course, we want to change the data, we want to balance the data set, but we want to change the data in a way that the utility of the data is not destroyed. And the utility is very important because this is what gives good predictive performance. It's very important for the learning task. So this means that we want to intervene at the data, but the intervention should be really minimal in order to not destroy the utility of the data. And there are many different approaches, from simple approaches like oversampling, undersampling, to careful sampling, approaches that use weighting, so coarse-sensitive learning, approaches that change the class label. This process is called massaging, approaches that augment the protected group, which is the minority group, by using synthetically generated instances. And many of these approaches, or most of these approaches, are actually heuristics, which means that it's not really easy to control and to control the impact of the different interventions. But of course, there are also more principled approaches. And here is an example of massaging. So the main idea here is that we want to change the class labels of carefully selected instances. So again, we have two classes here, the red and the black, and we have male and female instances. So the symbol here denotes the gender. And the idea is to apply this technique in order to change the class labels of carefully selected instances and swap their labels. So this is the so-called massaging technique, and the result of this technique is the corrected or the pre-processed data set, or the massage data set, in which, as we see, we have a more balanced representation of the different subgroups. The second category of methods are the so-called in-processing approaches. So the main idea here, or the main intuition here, is that if we want to change the behavior of the model, then we can do that by intervening directly at the algorithm. And by changing the algorithm that is used to learn the model, we have actually better control over the behavior of the model. And the idea, therefore, is to explicitly incorporate this fairness, so the measures that I mentioned before, in the objective function of the algorithm, which is typically optimized for predictive performance. And the design principle, or how people try to incorporate this information to the model, is again by taking care of the both predictive and fairness performance of the model. Right? So we want a model that has a good predictive performance and performs well also in terms of fairness. So these two components should be balanced, and I use the term balance here on purpose, right? So they should be combined in a way that one does not dominate the other. And there are different techniques here also, because these techniques really depend on the model, right? So if you have an SVM, for example, then it needs a different handling comparing to a neural network or comparing to a naive-Bayes classifier, etc. So there are a lot of approaches, from approaches which add a regularizer into the objective function to approaches that add fairness constraints and approaches that change the data distribution in training. So this is what the boosting approaches do, and approaches that assume, for example, that there are unbiased class labels which we don't know, so latent variables, and we try to find also these latent variables. So as I mentioned before, the idea here is to pay attention to both fairness and accuracy as part of the objective of the model. And one very common way is actually to combine fairness and accuracy loss into a single overall loss. So here you see the objective function. So we are looking for a model theta, which minimizes the loss. This is the typical accuracy loss, and the fairness loss. So the F is the fairness loss, and these two losses are actually aggregated using this lambda parameter, which is a weight parameter that determines this trade-off between fairness and accuracy, and is typically selected using hyperparameter tuning. So this is an approach to assume that there is such a trade-off and to make this trade-off explicit. Recently, however, there are a lot of papers, a lot of works which question the existence of such a trade-off. So do we really need such a trade-off? This is the question, especially since the goal of fairness-aware learning is to achieve good predictive performance for all the different subgroups. So these goals are not necessarily conflicting, or are not always conflicting. So in this direction, there are also approaches, that this recent work by Arjun and myself, in which we learn whether we should train for accuracy loss or for fairness loss. So we train a neural network here, and in each epoch we decide whether we should use the accuracy loss or the fairness loss, and this is something that we learn dynamically. And this means also that we optimize for accuracy or fairness dynamically over the training grounds. The third category of methods are the so-called post-processing approaches. So the main idea here is that we build a perfect model with respect to predictive performance. So this is the traditional machine learning. And then we try to tune this model for fairness, right? So first to optimize for predictive performance, and then we tune for fairness. And of course, while tuning for fairness, the idea is that we want to change this model so as to achieve these fairness requirements, but we don't want to destroy the good predictive performance of the model. So again, the interventions at the model should be minimal in order to retain its good predictive performance. Again, a lot of methods here, also because these methods are typically model specific. So there are approaches, for example, for decision trees, which correct the class labels, or approaches which shift the decision boundary, or approaches which correct the confidence scores, etc. So here is an example. On the left, we see a model which is optimized for predictive performance, and then on the right we see the correction or the tuning of this model so as also the fairness requirements are met. So many different approaches in order to mitigate bias. But it's not only about mitigating bias, it's also, there are also approaches, or there is a line of research which is in the direction of accounting for bias. And in this category, there are two approaches, or two categories of approaches: proactive approaches. So how can we proactively account for bias and discrimination? And typically, the solutions in this direction are with respect to data collection, so bias-aware data collection, but also with respect to documenting and reporting on data sets and models, how they were collected, how they were trained, etc. And the second category are the so-called retroactive approaches, where the idea here is that we can use explainable AI, so another important concept of trustworthy AI, of responsible AI. So we can use explanations in order to understand whether the decisions of a model are biased, and even further, we can use explanations in order to de-bias or correct the system, so the decisions are not biased. So let's start with the first category. So this proactive approach is to fairness-aware machine learning. So the idea here is that we want, during the data collection, we want to collect data in a way that considers possible biases with respect to different protected attributes. So this is an effort for visual data sets, and there are several attempts for bias-aware visual data collection. So you see here different data sets and the bias-aware collection with respect to specific protected attributes like gender, race, etc. And here is an example of such a data set, so the fair face, which was collected so as to be balanced with respect to 7 different race groups. So this is the fair face data set. You see the race distribution and also the comparison to other data set, right? So you see that it's more balanced. So of course, this is a nice direction, right? So collecting data, so while collecting data to ensure that you have a good representation of the different subgroups that you want to study. But of course, these data sets are collected for specific purposes, for example, with respect to the race, right? So they were balanced with respect to race or with respect to gender, etc., which means that they are not universally bias-free data sets, right? So this is important. And the second aspect is that pretty often these data sets are balanced with respect to their cardinality. So the goal is actually to have a similar amount of instances from the different subgroups, but this is not always sufficient. So the group variations might differ, and one might need also to consider these variations. So maybe some subgroups are harder to learn comparing to other subgroups. Another approach is this documentation, so reporting on how a model is trained and tested, and also reporting on the different data sets, how they were collected, for what purposes, etc. So one popular model reporting tool are the so-called model cards, and for data sets, a popular approach are the so-called data sets for data sets. So this is what a model reporting looks like for the model card looks like for a smiling detection in images. So this is a model built upon the Celebrity A dataset, and you see here different details on the model, what is the intended use, the different metrics that were used for the evaluation of the model. And if you look at these different metrics, you can see that not only the overall performance is reported, but also the performance across the different subgroups, for example, males, females, or combination of gender with age, etc. Right? So it's really important to report on the subgroups. And another approach in this direction of accountability are the so-called retroactive approaches. And as I mentioned before, explainability, right? So explaining the internal mechanism of a black box model in human understandable terms. And usually when we think about black box models, we think about neural networks, deep neural networks, but black boxes are also, for example, ensemble models, which are very popular and were popular also in the past, right? So this is a very important component to be able to explain how a model decides. And explainability is a very important tool and a very versatile tool because it can be used by different user groups. So simple users and users can use explainability in order to understand how a certain decision was made. For example, why I was selected for police inspection, but they can also check whether they are treated fairly, so in connection to fairness, or also whether they have some sort of actionability over the decision of the model, right? So how can I change, or what can I do differently, or how can I change my instance in order to get a positive outcome? So this allows for actionable insights and recommendations to the user in order to change the decision of a model. It's not only for simple users, it's also for users, professional users, which use AI in their jobs, so to ensure that the decisions are correct and in accordance to legal and societal standards. For example, there is no discrimination. And what is also very important is that explainability is a very important tool also for people developing this technology, because it gives us insights and allows us to inspect and debug these models to ensure that what the model has learned is robust. So is the system trained properly? Is it working as intended? So we need systems which make good decisions, right decisions, of course, but these right decisions should be also for the right reasons, right? So not based, for example, on the background, because all the training instances have a certain background. And of course, it's important to use this inspection and this debugging information in order to improve the performance of the model. So can we get through explainability insights on how to improve the performance of the model? Pretty often, this is the case. So here is an example of a hate speech classifier. So these are two texts or two documents which are classified as hate speech by a fine-tuned BERT classifier. And what you see here underlined are the words which contributed to this decision. And these are all words which are called group identity terms. So these are terms regarding ethnicity, regarding religion, regarding sexual orientation, etc. So words that should not be used for the decision making. So these are words which point or lead to discrimination. And the question now is that, the first step is, of course, to detect whether there is the classifier is oversensitive to such group identity terms, and it shouldn't be, right? So this is the first step, to see whether the classifier is biased towards these group identity terms. And the next step is, of course, to debug the model, so to remove this oversensitivity of the model to the specific terms. And of course, the easiest approach here would be to remove the identity terms, but this is not sufficient. And a better approach is actually to try to control the contribution of these terms, or to suppress the contribution of these terms. So the explanations in this case could be used also as part of the objective of the model in order to regularize the behavior of the model, to not pay so much attention to these words. And here we see the result of the model before the correction, so before the debiasing, and after the debiasing. So before the debiasing, we see that the model pays attention to protected terms, and it shouldn't. And after the debiasing, we see actually that the model makes a decision using the correct terms. So it's not overemphasizing these protected terms. And thus far in my talk, I referred to the simple fairness-aware learning setup, where we have a single protected attribute, what we call monodiscrimination or single discrimination or one-dimensional discrimination. But as we know, humans have many identities, right? So as humans, we have many identities. Some of them are protected, for example, race, gender, age, religion, etc. Some of them are non-protected. And of course, with algorithmic decisions and with every decision making, we want to be sure that these decisions are fair with respect to the many different protected dimensions, right? So this single dimensional fairness-aware learning is not sufficient because humans are multidimensional and discrimination might be due to many different protected attributes. And I mentioned at the beginning that there is a lot of work in this area despite the recency of the domain, but actually most of the work focuses really on this simplistic case, so one protected attribute, and does not handle these multi-discrimination cases. And moreover, the majority of the methods focus on tabular data, so this is another limitation, I think, or another, let's say, direction for future work, so working with different data types, as the majority of the works, at least in supervised learning, really focuses on tabular data. So what is the multidimensional fairness and why it's challenging? I mean, why you cannot just use methods from the single dimensional fairness-aware learning domain, right? So just use these methods for the multidimensional fairness domain. And it turns out that if we reduce discrimination with respect to one attribute, for example, gender, then this will not necessarily decrease discrimination also for other attributes, for example, race. In some cases, it might even increase the discrimination, right? So we cannot really hope that by just correcting for one attribute, we'll also correct for all the different attributes. So a joint consideration of the different attributes is needed. And moreover, the simple approach where we train a classifier to be fair with respect to the different protected attributes, so fair with respect to gender, fair with respect to race, fair with respect to age, is not sufficient because in this case, we don't pay attention to the subgroups, so to groups which are created by the intersection of the different protected attributes. So this is a so-called fairness gerrymandering problem, which means that we should really focus on the subgroups which are created by the intersection of the many different protected attributes. And as we create these subgroups now, we have a data scarcity problem, and there are two different flavors of this data scarcity problem. First of all, we might have population imbalance, so some of these groups become very small, or they might even become empty, so we don't have any instances, let's say, for old Black females, whereas we have a lot of instances for young white males, right? So we have a population imbalance across the different subgroups. And moreover, since we talk here about supervised learning, so we talk about class, also information is important, we might have class imbalance and different class imbalance in the different subgroups. So for some of these minority subgroups, for example, the old Black females, we might have really a severe imbalance with respect to the positive versus negative class, right? So we have different flavors, let's say, of imbalance in these intersectional subgroups. So let's take a closer look to this fairness gerrymandering problem that I mentioned. So here we have a hypothetical classifier which is trained to be fair with respect to race and to be fair with respect to gender, but does not look at the intersectional, at the groups created by the intersection of these two attributes. And we see the performance of this classifier with respect to the ground truth. So we have the predictions here, so the false negatives, the false positives, true negatives. And starting from left to right, we see that in this population, we have a majority Black population. So most of the instances come from the Black population. And if we consider the gender, we see that the Black males are a majority, followed by white males, Black females, and then white females. And if we look now at the predictions, we see actually, especially for the true positives, so typically the positive class is the most important class. In the true positive, so in the true positive subgroup, we see actually that we have contribution from only 3 out of the 4 subgroups. So we have white females, we have black males, and we have white males, but we have no black female classified as positive, right? So the black females do not contribute at all in this subgroup of true positives. So no positive decision for black females. And therefore it's really important to focus at these intersectional groups. So just correcting for race and correcting for gender is not sufficient. We should really pay attention to these subgroups. So this intersectionality notion of fairness. And I mentioned before the problem with the data scarcity and the 2 flavors of data scarcity. And let's take a closer look to an example which comes from the adult income prediction dataset. So this is a dataset that is used very often or almost always in fairness-aware learning. So it's about predicting whether someone will have an income higher than 50K. And what you see here is the different subgroups created based on 3 protected attributes: gender, race, and age. And you see the cardinality of 2 of these subgroups. So the black young female subgroup consists of 555 instances, whereas the white old male subgroup has 40 times more instances, so 22,856 instances, right? So you have what I mentioned before as population imbalance, so some subgroups are really small comparing to others, which means that when we try to learn a model upon this population, these subgroups will be actually not very visible to the model, right? So this is where we have to actually pay attention to. And moreover, if we look now at the imbalance, at the class ratio in these subgroups, and I have here only the numbers for the smaller for the smaller subgroup, we see that there is an extreme class imbalance. So only 9 out of the 555 instances are positive, which means that we have really a severe class imbalance in this minority subgroup. So these are the two main problems with respect to data scarcity, right? So population imbalance, different subgroups have different cardinalities, and also there is extreme class imbalance, and this extreme imbalance is even more extreme or even more severe for the minority subgroups. And this is the case also for other data sets. So these are 2 more data sets, so the bank and the credit data set, and you see here the class imbalance ratios, so positive versus negative instances. So we have class imbalance in all of these data sets. And also you see the group imbalance ratio, so protected positive versus non-protected positive in the minority class, in the positive class. And you see that for some of these protected attributes, the protected group in the minority class, it's actually underrepresented. Look here at the age, for example, 1 to 23 for the bank data set, right? So we have a severe class imbalance for the in these subgroups with respect to the protected subgroup. And there are ways to deal with class imbalance. I mean, this is another old problem in machine learning, right? So there are a lot of approaches on how can we work if we have imbalanced data. But it turns out that if we deal with imbalance but ignore fairness, then actually the problem of discrimination might become even worse. So here we see the disparate mistreatment, so the fairness-related behavior of the model after applying smooth boost, which is an approach for dealing with class imbalance. And we see that after applying smooth boost, so ignoring the discrimination, just applying smooth boost to correct for the class imbalance, we see actually that the discrimination increases, right? So this shows actually that we cannot really tackle these 2 problems independently. We need solutions that consider both imbalance and unfairness or discrimination. And regarding the multidimensional discrimination, so this is kind of a more recent domain, right, or subdomain in fairness-aware machine learning. So there are only a few works, and most of these works ignore the class imbalance. So in these works, for example, they pay attention to the subgroups defined based on the intersection of different protected attributes, but they ignore the class imbalance, and we saw that we have severe class imbalance in the subgroups, which cannot be ignored. And there are also more recent approaches. This is one approach by Arjun and myself, where we also consider not only the class imbalance, but we consider not only the many protected attributes, but also the class imbalance. And the idea is to minimize the discrimination of the most discriminated group defined based on a protected attribute and a class. So what we call here the multi-max mistreatment measure. Good. So this is ongoing work, and it's actually part of the work that we are recently started as part of a European project on multi-fairness and multi-discrimination, so the Mammoth project. So we are looking forward to more results in this area. So I think I'm done for the moment, right? So I just want to wrap up, right? So I think it's clear that algorithmic objectivity is a myth, right? So we have bias and discrimination in AI system, and we have bias and discrimination in our society. So humans are biased, data and algorithms are also biased. And bias is not caused by AI systems, or is not caused only by AI systems. We contribute to this bias through the data that we use to train these systems, through the systems that we build, through the algorithms that we create, etc. The good thing is that after so since the beginning of the domain, there is a common understanding on several aspects. For example, that technical fixes are not sufficient. We can fix the algorithm, but the society, so the humans, we should be also not fixed exactly, but I mean, we are also biased, so we should really consider fixing bias in the society also. And on the positive side, I think the technology can help us also to reflect on our own biases. So if we see bias in word embeddings, for example, and it's clear that this bias comes from the society, then this is also a good reflection mechanism to think, okay, what sort of content do I provide in the web, how I use the language, etc. So I think it's hopefully helping also the humans to become less biased and more fair. We also agree, there is also an agreement that fairness cannot be reduced to a single definition, because the different definitions of fairness make sense for different contexts. Fair is not fair everywhere, and it's a moving target, which means that we should be always kind of proactively and retroactively look for biases and discrimination in our systems. Bias depends on context, and it's not always easy for a machine to understand this context, right? So I think this is one of the big problems with artificial intelligence. So understanding the context, like in these examples here. So you need some background knowledge to understand what is the problem with this image, and what is the problem with this image with respect to bias and discrimination. In terms of the domain, so fairness-aware machine learning, there is a lot of work, but as I mentioned, most of this work really focuses on simple scenarios, and the reality is much more complex, much more demanding. So we have, for example, multi-discrimination, we have different data modalities or even multimodal data. We have additional challenges, right, like class imbalance, distribution shifts, etc. And also we have to rethink evaluation. I mean, all of these methods thoughts, do some sort of intervention, and then we keep testing our systems or our algorithms in the traditional way, using the training testing approach. Maybe we need to rethink the evaluation and really consider these long-term effects of fairness interventions. We need better data sets, so we always use the same data sets. I mentioned adult as an example. This is a very old data set. There is a new version recently which is supposed to replace this data set, but we need more realistic data sets. We need benchmark data sets, and we need also evaluation of the different algorithms to understand really how they compare to each other, for which problems they perform well, for which problems they do not perform well, where should we focus our attention, right? So what sort of methods we need to build, etc. And of course, we need to be aware of this bias and discrimination. So everyone working with data scientists, our students also should really be aware that all our decisions might adhere to this bias and discrimination, from simple decisions like pre-processing or discretizing the data, etc. Right? We should really reflect and be aware of our choices, or of choices that the different frameworks that we use make for us, without even realizing that there is something else happening behind calling a function. And I think we need responsible AI, and I think it's also very important that we treat this technology, the development and also the application, the deployment of this technology with responsibility, because the technology is very powerful and there are many different applications and usages of the technology. How we use it, for what purpose we use it, this is very important. And of course, it's very important to build teams that are that have different characteristics, right? As I mentioned in the beginning, bias is of human nature because the majority does not have any clues about the needs and about the requirements of the minority, right? So the minority, all the minorities from women to people of color, etc., they should be in the table. They should contribute in developing this technology. And there are different ways to improve the technology, right? So as I mentioned before, from really being aware of our choices and better implementing the technology and reflecting on our choices, even small decisions matter, to thinking proactively what sort of data I collect, documenting the data, documenting the models, etc., to fairness-aware learning, so explicitly targeting fairness and discrimination through different, and there are many fairness-aware learning techniques, using XAI to ensure that the system learns the right thing, or you have some control over what the system has learned, interactive AI, resilient machine learning. So there are many different aspects. All of them are very, very important. So my point is that we have some tools. They are not perfect, but we should use them, right? So we should really start working in a more responsible way. And this includes also the daily practices in our data science related activities. Yeah, so that's all from my side. Thank you very much, and to all the different, of course, funding bodies that support our research.
Yeah, thank you very much, Irini, for this great talk. We have time for a few questions. So maybe I will start with the first one. So, I mean, is the research on, because what you could do, you could try to make your model, like have one model for all and try to make it as fair as possible, or you could try to train more personalized models, or trying to train a model for each subgroup. Mm-hmm. What are the trade-offs of there?
Mm-hmm. So there are some approaches actually which really try to build models for the different population subgroups. For example, one model for males, one model for females. And the question then is that you make this decision about how to treat fairness during the decision making, right? Because you have two different models and you should use them for decision making. So how do you combine them in the final decision making? And with respect to the multi-fairness aspect, as I mentioned, one of the major problems for machine learning is the lack of data, right? So some of these subgroups do not have sufficient data, which means that the model that you learn from the subgroup will not be very very good, right? Of course, there are ways, right? So you could kind of try to use information. So like in multitask learning, try to use information or transfer information from other subgroups, but still you don't have sufficient evidence, sufficient instances from this population subgroups. So there are also, let's say, yes, challenges with respect to the data.
And you also like presented very nicely like this relations between XAI and fairness, but I think that there are also like other aspects, right? There is robustness, there is like interpretability, accuracy, fairness. So can we kind of optimize all of them, or like how can we how can we try to like really embrace it, because then things become even more complicated?
Yes. So interestingly, there is now this, there are some works recently on ensuring fairness and privacy, right? Because with fairness-aware learning, you try to make these subgroups kind of more visible to the model, and this comes in contradiction to what with the privacy-aware learning, right? Where you try really to hide the individuals to not reveal their identities. So there are approaches in this direction. I think this is really important, but as you said, becomes harder, and there are different, there are some conflicting goals maybe. I mean, it's not, I'm not really sure, or I cannot say because I haven't worked in this area whether the goals are necessarily conflicting, but one I think solution that might be interesting in this direction, because we have so many different objectives, might also be to develop this multi-objective optimization, to follow this multi-objective optimization approach, and instead of a single model, to really have like a pool of models. All of them are optimal in the sense that they belong to the Pareto front. And then the question, of course, is which model the user can choose if he or she has to make one choice. But at least I think you have the option to see all these different possibilities, because probably you cannot have a model that is optimal with respect to all these objectives. But maybe you have models which are good with respect to some objectives, and looking at this multi-objective space and the different models might be actually useful instead of making a hard decision. Maybe this is something that the end user, or based on the application, can decide about which model is best for the particular needs.
And like last question from my side, can like fairness measures change, or like maybe new fairness measures like emerge? So can you make a model fair like post hoc, like after training, and then maybe you realize later that there is a subgroup which you haven't think of before? So what do you do post hoc?
So I think these are the so-called post processing approaches, right? Where the idea is that you have a model, and then you can tune this model for fairness. And of course, if your definition of fairness changes, because I mean, as I mentioned, right, fairness is like a moving target. Maybe we have a different concept of fairness tomorrow, or as you said, maybe there is an attribute which has not been considered as far. Then I think this could be an idea, right? So to apply the new fairness concept after. So this could be an idea.
And maybe another one last question. Do you know of any like real systems where these fairness measures are already like in place, or is it like more still at this academic stage where people are talking about it, or is it like real out there?
I mean, what is reality? No, I'm joking. I mean, there are some frameworks, like for example, one created by IBM, or initiated by IBM, so the 360 fairness framework. So there are some tools, and there are some tools which you can easily use I mean, maybe not, yes, maybe some informed, let's say, user with respect to data science aspects. So there are some tools out there. I think the main problem with these tools, and probably this is because this is a very new domain and it's changing very, very fast, right? The main problem is that there are no clear benchmarks. So in terms of data sets, which data sets to use for evaluation, what to evaluate, what to report, right? So different people report different things. So you don't have any concrete idea about which method performs well, right? So I think this is very important, I think, because we keep proposing new methods, new algorithms, and we don't have a good way to compare their performance to other algorithms, right? So I think this is something that is missing from the field. So data sets, measures what to evaluate, and also in terms of methods, I mean, what are the competitors, right? So in other domains, I think this is, but of course they are much longer, right? So they are older domains. I think this is, yeah, there are domains where this is clear, and I think this helps the sustainable development of the domain, right? So I think this is a big problem now. And as I mentioned also, I mean, moving from this really basic setup, because it will never occur in reality, or the reality is much more complex. Of course, this makes sense in terms of development. So we start from the simplest case, and then we kind of increase the complexity. But I think it's really time to kind of think of increasing the complexity. And there are different ways. So moving to more attributes, or considering other data types, or considering multimodal data. Considering other learning tasks, right? It's not only supervised learning, although there are words also in unsupervised learning. I mean, I haven't covered all of them, so I'm mainly focused on supervised learning. But I mean, we need also really to work on more challenging, let's say, problems. And in terms of explanations, I mean, you are an expert, right? I think my main concern, or my main concern with explanations is that explanations are also not a panacea, right? When you build, for example, when you build these LIME explanations, right? There are so many assumptions how you find the neighborhood for the local explainability models, and I think, yes, the explanations are very important, but they are not the only truth, to my understanding, right? So they give you some insight.
We also have the same problems with how to evaluate, what are the data set, what are the measures. So we're actively working on it, but I think these fields have similar
problems.
Okay.
Yes. So, yeah. I think, I mean, there are problems in all the methods, that's clear, and people work to improve these aspects, that's clear. But I think this is not an excuse to kind of, right? So you should use explainability because it helps you to get some insights. It's not the only truth, but it gives you some information. Likewise for fairness, the methods are not perfect, but at least you have to check how it performs, for example, for the different genders. Can I do something to improve the performance, right? So this is what I mean, that we have no excuse despite the non-perfect methods.
I fully agree. Yeah, so thank you very much, Irina. It was really an inspiring talk, and yeah, best regards to Munich. Bye-bye.
Bye, thank you.
In today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
you.